You can see clearly that although you don't like to make compromises, there's many different modes, many different conflicting terms to kind of find the right position.
When we made the transition from displacement of boats that were floating to boats that were foiling and flying, the design team configurations changed as well, because back in the day, full of naval architects and structural engineers, but slowly the design teams, the configuration changed, and now 80% is more aeronautical engineers. So the boat is 80% airplane, 20% boat. The principles that guide aircraft design, position of center of gravity, relative position of the wings, size of the wings, aspect ratio, it's pretty much the same we do here. So also we have these wings which operate in water, but also the sails are wings in itself. So we have vertical wings and we have horizontal wings, and they're all control surfaces that we need to move to adjust to maximize the performance.
20 years ago, flying at Mach 7.5, 7.7 was good. The last decade, sort of 0.885, and now we're in the sort of good ranges at 9.0. A little while back, to clear the way for the Global 8000, we did a supersonic flight. We did a flight beyond Mach 1. The wing design in itself had a lot of features inbuilt to kind of show that split ailerons, because there's all sorts of things that happen in terms of things like reversals and stuff that you have to make sure you manage for. If I look at your foiler, is there like a 50 knot squall? Is there something where it starts to get interesting and you get cavitation? Or you gotta go see smiles.
No, well, we have our own speed of sound, which is cavitation speed.
Yeah.
If we want to perform under cavitation speed, we cannot perform over cavitation speed. So it's one of the big compromises we have to.
Yeah. Because these boats get to cavitation very early, and in the past you needed 20 knots of wind speed to get there. Now we get there very early because the boats are very fast. So yeah, it's a good discussion. It could go for months. Just going for months.
And the methods and models we have to predict cavitation are extremely accurate. But what we need to work on is the compromise we were talking about,
I guess, as you said, this modern generation of foilers get to that speed pretty impressively.
3 years ago, thinking about 50 knots was, you couldn't even think about 50 knots. Now you're going 50 knots, so it's very fast.
And if you don't have cavitation, you're not pushing enough.
It's a bit like a lot of things, which is it's about finding the right boundary. The actual sail itself looks very impressive.
The sails are like Morphy wings. That's the beauty of the soft sails.
So you can change camber on them?
Yeah, we change camber, we change drag, we change angle of attack. So we can do pretty much anything. And as you go through the speed range, you go from very full sails to super flat sails. And so then we have our software, fluid structure interaction softwares, where we put the structure in the sails so they behave. Then because they need to have a huge range. All the components are designed to the minimum safety factors, minimum. That's why we go out, we break things, we return, we beef up a bit of components.
It's a little bit like cavitation, we need to have cavitation to make sure we are pushing. We need to be just reliable enough.
It's not like you have a 20 or 30 year life cycle.
No, and there's short races, but yeah.
Us here, it's been educational. I look at some of the work that we're doing in our next generation of aircraft, the EcoJet, which is a blended wing body configuration. I look at the shape, particularly of the underside of your foiler, and it's kind of a step change and makes us learn maybe some of the stuff that's not in the books or behave.
Yeah.
But I thank you for hosting us. I will let you get back to the important event, and wish you much luck and safe sailing.
Thank you for coming.
Pleasure.
It's been a great chat, and thanks for supporting us.
Absolute pleasure. We support.